Hello student to the foundation of classical electrodynamics course. Under module 2 today we will going to have the lecture on quadrupole moment. In the last class we discussed in detail about the calculation of the monopole moment and dipole moment. Now in today's class we will discuss about the quadrupole moment. So we have class number 36 today, and today's discussion is on the quadrupole moment. So, let us go back to the calculation we started in few classes ago, that if I have a charge distribution and this is some reference coordinate system, this is R, this was R prime, and this was curly R. This is a system where the charge distribution is defined as rho prime, and when we write the potential, if you remember the potential at point, say at this is P point, the potential and this is at R, the potential at R was this. The first few term, if I simply write the first few term, it should be like 1 by 4 pi epsilon 0, and then I had the first term 1 by R and the integration of rho R prime dv prime. That was the first term. So, the second term was 1 by R square then integration of R prime cos theta and then rho R prime and then dv prime, and then I had 1 divided by R cube integration of R prime square and with the half term, and then 3 of cos square theta prime minus 1 rho R prime dv prime, and so on. So, I have already discussed this first two case. This if I write, so I should write at phi r is the contribution, the first term is the contribution of monopole second term is the contribution of dipole, and third term should be the contribution of the quadrupole. So, now this term I am going to calculate and try to understand what is the meaning of this term. So, phi 3 or phi quadrupole. So, if this is my phi 1, phi 2 according to our old notation, phi 3. So, the quadrupole contribution phi 3 was, let me write it once again, 1 by 4 pi epsilon 0, 1 divided by r cube, then integration of r prime square and then I should write in terms of Legendre polynomial, it was p2 cos theta and then rho r prime dv prime. That was the entire term over the volume integral V. What was p2? p2 is a Legendre polynomial of order 2 cos theta. This term is half 3 cos square theta minus 1. So I can divide from these two. I can define okay, let me simplify few things. So my phi 3 is now 1 by 4 pi epsilon naught and then 1 divided by 2 r cube integration of r prime square and 3 cos square theta minus 1. I am writing the same term once again, but now I will deal with this cos square theta term, because we know that the r dot r prime is r prime cos theta. So cos theta I can remove in this way, that it is nothing but the square of r dot, and if I do, then it should be like this. So phi 3, I rearrange the term like this: 1 divided by 4 pi epsilon 0, the constant term, 1 divided by, so in order to introduce the cos theta, I need to multiply the r square here, and then I divide the r square, so it should be r to the power 5, then integration, then this cos r, now I multiply r square, so this term will be 3 and then multiplication of r dot r prime square. So 1 r square is here, so which is taken care of this r to the power 5, and another term should here also, and that is r square and then r prime square, and I have rho usual term and dv. Okay, so now I can define my quadrupole term here, whatever I had, but before that let us try to understand what is r dot r prime. So in if I consider the Cartesian coordinate system in Cartesian coordinate system, so x component now on I should write as x1, y I should write as x2, and z I write at x3. So what I should write for r dot r prime in terms of x, y, z, and that value, if I look carefully, r dot r prime is simply xi prime, because dot, this is the way we write, and square of that, and if I expand this, then it should be xi prime multiplication of xj prime, because when we have a multiplication the cross term will be there. Mind it, this is a repetitive index, so one summation sign is there, so that you should remember always. So otherwise you can just check it like this way. So r dot r prime is simply x1 prime plus x2 prime plus x3 prime. Now if you make a square of that, then all the other cross term will be there. So that's why this I and j need to be here. This is the shorthand notation, Einstein notation, that's why I write it. But you can check it. Now if you make a square of this quantity in the left hand side, then in the right hand side whatever you have, you make a square, and when you make a square you have the cross term, or this multiplication the same term, you will going to get a cross term, and that term will be simply summation of xi prime xj prime, and the summation is over I and j. There are double summations are there. So now this r dot r square is represented in this way. So what about r square and r prime square? Now r square and r prime square, this term is simply, say if I write in terms of r prime square, it is r prime square and r is xi, r square is xi. So I can write it r prime square xi xj, because already xij is there, and delta ij. This is the way I can write it, right. So my phi 3 which is a function of r is simply 1 divided by 4 pi epsilon naught, and if I write in component wise, so let me write in an explicit way, I and j, and then I have xi xj divided by 2 r to the power 5. I take xi xj common, because here in this term I have one xi xj, and here in this term I find that I can write in xi xj with the delta function, and then I take it common. So this quantity, then integration, I take xi xj out of the integration, because this is not prime and the integration is over prime. So it should be 3 xi prime xj prime and minus r square, r prime square rather, and then delta ij bracket close, rho r prime as usual dv prime. This is over dv. Now I am in a position to define the quadrupole moment, and you can see that there are 2 primes are associated with that to define the component of the quadrupole moment. So that means it is not a vector, it should be a tensor quantity. So this is I. So I summation of j xi xj divided by r to the power 5, and rest of the term I write as qij. This is the quadrupole term, this qij, and you can see that this is a this comes up to be the tensor quantity. So, now Qij, we will now concentrate only this term, is equal to half of integration over the volume 3 xi prime xj prime minus delta ij r prime square bracket close rho r prime dv prime. So, this is the value of the quadrupole tensor, and this is the value, this is the ij component. So, there should be 9 components like this. So, this is Qij is our quadrupole tensor. So, if I write the total value, so Qij, if I write my total Q, that is this one, Q11, Q12, because I can take 1 2 3, J can take 1 2 3. So, I should have this value Q21, Q22, Q23, Q31, Q32 and Q33. Okay, fine. But also I have another important information, and that is the symmetry. The symmetry is, you can see that Qij is equal to Qji. That means, if you just replace I to j here, if I just replace I to j and j to I, then there will be no change actually. This will be the same like the before. So, Qij and Qji should be same. So, that quantity is Qji as well. Not only that, this is one important thing. So, this is a symmetric tensor. Another important thing, if I now check the trace of this matrix, whatever the matrix we are having right now, that is Qii sum over I 1 2 3, then that value is 0. So, this is traceless. So, I can prove that, because I mean, let me quickly show it. So, Q11 plus Q22 plus Q33, these are the diagonal terms, and if I add all these diagonal terms, then that quantity is called trace, and this value has to be 0 here. So, if I add over all I, so I only take the value when I equal to j and then sum over I. So, I, and I take this quantity which is 3 x I, and I take x I because I and j are same here. So, this is prime minus r prime square, it will remain like this, and delta is I. So, that is 1, and then I have rho r prime and dv prime. So, now I make a summation over I 1 to 3. So, when I make a summation I 1 to 3, what you will going to expect is, let us take half outside and let us put this integration inside. So, then you will have 3 and this integration is over only this term. So, it should be xi prime I goes to 1 to 3 and then minus, okay, let us put delta II here for convenience, and then r prime square and this sum over delta II, again I can goes to 1 to 3, okay, and over rho r prime dv prime. So, this quantity again we calculated earlier, right? This should be 3, and what is this quantity? What is this quantity? Summation of xi xi prime, sorry, it is not, it is both the cases it is prime. So, I miss this prime here, I miss this prime here. So, xi prime multiplied by xi prime is 1 to 3 is simply x1 prime plus x2 prime plus x3 prime. This is nothing but x1 prime square plus x2 prime square plus x3 prime square, which is nothing but r prime square, because r prime is x1 prime x unit vector plus x2 prime y unit vector plus x3 prime z unit vector. Okay. So, after having that, we are almost done, because this quantity comes out to be 3r square and already 3r is here. So, eventually what I get is q11 plus q22 plus q33 is equal to right hand side half integration 3 r prime square plus 3, sorry, there is a minus sign, minus 3 r prime square, let us, because this is a very important minus sign. So, I should not mess up here, and then bracket close rho r prime dv prime, and this quantity is simply 0. So, that tells us that the summation over I q I is 0. That means the tensor is simply traceless, whatever the quadrupole tensor you have. So, whenever you calculate the quadrupole moment, this tensor should have a this matrix should have a it is a traceless matrix. The trace should not be non-zero, it is 0, and also it is symmetric. So, there are many relation between the q11, q1 to q13. Once you find one value, then they are not independent. So, there are the relation, two very important relation we are having, that they are symmetric and traceless. When you calculate, then this information will going to help us. So, let us jot down what we have so far, because this is important. So, let us jot down what we have so far in few classes, in last few classes, and then we are going to proceed. We maybe calculate, if time permits today, we will going to calculate the quadrupole moment for a given charge distribution. So, moments. So, what we find is moments of general charge distribution. Moments of general charge distribution. So, I have two kind of, we discuss about two kind of charge distribution. One is the, for first case it is say for discrete charge distribution. For discrete charge distribution. So, for discrete charge distribution, if I visualize, I should have a coordinate system like this, and I have the charge particle q1, q2, q3, q4, etc., qk, like randomly distributed. So, this is my coordinate system, and so this is the qkth charge, and the location is rk. Similarly, you have q1, q2, q3 and so on, okay, but location of this is rk. So, if that is the geometry of the charge distribution, then one by one let us write. So, the moments so the first I should have the monopole moment. So, in monopole moment, what we find that q is equal to sum over qk, k goes to 1 to n, that is nothing but the total charge. That is the way we define the monopole moment. Second thing, for discrete charge, this is the way we define. Second thing is dipole moment. The dipole moment P, this is the way we write dipole, is defined by sum over k equal to 1 to n and qk rk this. This is the way we define the dipole moment. Please mind it, the dipole moment now defined for a system of charges. This is not one charge, this is n number of charges is there, and still I can define the dipole moment. So, if you have an impression in your mind that dipole is only consist of two plus and minus things, so this is a one kind of dipole, but in general, if you don't have the if you have a charge distribution, still I can have the dipole moment, and you can check it for two values whether this general definition is fine or not. So, let me do this so that there should not be any confusion. That suppose you have two charge equal and opposite, that is the condition you need to put. So, so let us have the coordinate. Say this is R2 and this is R1, and this charge is say this charge is say minus q and this is plus q, right. So, according to this I have P is equal to summation of k equal to 1 to 2, because two charge particles are there, and then qk and then rk, that is, so that means I have q plus q R1 minus Q R2. So, this is Q R1 minus R2, and R1 minus R2 is this vector. Okay. So, or okay, it is from opposite direction. So it is from minus to plus. So, this is the direction. So, I should have, if this is my D vector, then it is simply Q D vector. That is the general definition we had, that the separation between two charge particle, two charge quantity having equal and opposite charge, 2 point charge having the equal and opposite value, and the distance between these two is, if it is D, then we have. So, from here you can see that even from this definition I can get this. And finally, for discrete charge I can have the definition for quadrupole moment. So, quadrupole moment is Q I j for discrete charge. It should be summation Q k divided by 2, the sum over k, which is say 1 to n particle, n charge particle, and then I have 3 x I, this is the kth charge particle, x j, this is the for kth charge particle, and then minus of mod of r k square and delta I j, that was already there. So, r k is defined like x 1, this is the kth r. So, that is why I put a x unit vector plus x 2 k y unit vector plus x 3 k z unit vector. This is the way it is defined. Now, we will write down what happened for continuous charge distribution. And now, for continuous charge distribution, so we have a coordinate like this, and here this is the charge distribution we have, and this is defined by rho r prime, and this is the location of that small section, and this is r prime. Okay. So, now the monopole moment quickly. First, the monopole moment will be defined by q is equal to integration of rho r prime dv, which is nothing but the total charge. Second is dipole moment, which is p unit vector, and that we know, that is v r prime, and then rho r prime dv prime, and finally the quadrupole moment, which we discussed today in detail. So quadrupole moment in continuous case, it is q I j, that is half of, sometimes in few books you find this half is not there, but anyway 3 I 3 j minus r prime square delta I j, and then I have rho r prime dv prime. So this is the overall gist of the moments for discrete charge and for continuous charge distribution. So I don't have much time today to discuss further. So in the next class maybe I will like to discuss about one problem where we calculate the quadrupole moment exploiting this expression which is now there in the screen, and then maybe we discuss more about if you once you do the problem, then you can understand that how the quadrupole moment can be calculated, and then we will going to end our discussion on this moment. But before ending, we will also show that how as I mentioned that when the charge is equal to 0, the dipole moment does not depends on the how the dipole moment depends on this coordinate for total charge equal to 0. So with that note, I would like to conclude today's class. So hope you can able to solve few problems, and then based on these formulas, and in the textbooks you have many problems, and please solve these problems. And with that note, I like to conclude today. Thank you.